So this next video is going to be for our multi-stage momentum problems. And so what's kind of interesting about two of these problems is momentum's only partially conserved for them. It's not entirely conserved. And so you'll see what I mean in a second. But the other thing that's interesting about these problems is that they have multiple stages to them. So there are portions where we're conserving momentum, and there are portions where we're conserving energy, and we have to work through both of those in order to solve the entire problem. So let's jump into the first question. So this question says a small block of mass m is at rest on a frictionless surface, is attached to a spring with a spring constant k. In an instantaneous explosion, it explodes into two pieces. The heavier piece, mass 2/3 m, goes off at a known angle of phi, as shown. Its motion is in the plane of the paper. The lighter piece goes off to the left, compressing the spring to a maximum amount. The spring gets compressed, given to be a. Find the velocity of the two pieces just after the explosion. Okay, so what we know here is we have this state of the system. So let's draw our before case. So here's our before, and we have this block that is ultimately going to be broken into two pieces. So this is going to be the piece, the bigger piece is the one that flies off at the angle. So this is going to be m/3, and this is going to be 2/3 m. Okay, and so right after the explosion, we have some velocity. We'll call this v. Let's see how it's defined in the problem here. So we have this velocity v1, let's call this, and then we have this one right here that is going to fly off at some velocity we'll call v2. Okay, so this is the after case, but then there's the after case, so like the third case that we have, where this v1 is going to compress a spring. So this v1 is going to compress a spring by a certain amount. And so this compression of this spring is given by distance of a. And so what we want to do is we want to determine what the velocities are, this v1 and v2. Okay, so we know that momentum is going to be conserved here, between here, p is conserved. And for our mass that is going to be a third of the mass, energy is conserved between these two. Energy is conserved, okay? So let's go ahead and set this up. And like I said, momentum is only partially conserved here. It's not going to be conserved in the y direction, right? Because there's no momentum in y in this initial state, but then there is momentum in y here. So what that means is that the floor is providing some kind of force, or the floor gets dampening for this recoil. It recoils actually in the y direction to compensate for this velocity that it picks up in y. So we're going to conserve momentum between this state and this state only in the x direction. So that's to say that the sum of the momentum before in x is going to be equal to the sum of momentum after in x. So initially, what's happening here is kind of boring. It's just sitting there. Nothing's happening. And this is going to be equal to this mass mv1, m1v1, minus, so that's with a minus sign because I'm going to say that this is going to be the plus x direction. This is the plus y direction. Plus m2v2 times sine of theta. So this gives us some relationship between our velocities for our two chunks here from conservation of momentum. But we just need one more equation here, and we're going to get that one from conservation of energy. So this is going to be equal to m2v2 sine of theta. And I'll plug in what I have for these masses actually a little bit later. So this is the first equation that we have that's going to be important. The next equation that we're going to have comes from our energy conservation. And so from our energy conservation, we can draw bar charts if we want. We can say that we have all kinetic energy. So this is all kinetic energy and no spring potential energy. And then this goes to no kinetic energy to all spring potential energy. So this says 1/2 m2 v this is V1, M1. M1 V1 squared is going to be equal to 1/2 K A squared. And so from this, what we can do is we can determine an equation for V1. So this says that V1 is going to be equal to the square root of K divided by M1 times A, which is equal to, this is going to be equal to the square root of M1 is going to be the one that has a third. So this is going to be 3K over M times A. Okay, so that gives us what V1 is going to be. And in order to find V2, we just rearrange this equation here. So we have M over 3 V1 is equal to 2/3 M times V2 sine of theta. We can cancel this factor of 3. We can cancel an M. This tells us that V2 is going to be equal to V1 over sine of theta, which says then that V2 is going to be 1 over sine of theta, or we could rearrange this like this even if we wanted to. So we could say that this is going to be, we have a factor of 2 in the denominator here. Don't want to lose that. So this is going to be square root 3K over M A divided by 2 sine of theta. And we have our 2 velocities. Okay, so I'm going to move this around and we'll move on to the next question. So the next question we have, again, kind of a similar situation, the fact that we're going to have to conserve momentum and energy between the states. And momentum is not completely conserved in this case, as we'll see in the y direction. So this one says a small block of mass m is released from rest on a frictionless track. At the bottom of the track, it goes into a box of mass m. The box with the block moves along a frictionless surface a distance of s. Starting at the point marked 0, there's friction between the box and the surface with a coefficient of friction of mu. If the box is to stop right at the point a distance L from the point 0, what must be the height h? Okay, so let's draw our before. And actually, I'm just gonna write these in terms of numbering the states. So here's state 1, state 2. So state 1, we're going to have this block on the inclined plane. And this is going to be some height of h above. This is going to be here. State 2 is, this is going to be just the instant before it gets in the box, in the box. Okay. State 3. So this is going to be moving with some velocity here. Let's call this V2. State 3, this is going to be in here now. This is moving along with some velocity V3. So I have a surface here. And then state 4, this is going to have gone some distance of d. And this is going to have come to a stop. So here's our mass of m. This is our mass capital M. Same thing here, m, 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 and then capital M. Okay, so that's the whole thing. So in order to do this, what we want to do is we want to relate first state 1 and state 2. These are going to be related via conservation of energy. Then relate state 2 to state 3. This is going to be partially momentum conservation. And then from state 3 to state 4 is energy conservation. Okay? So to write the energy in state 1, we have gravitational potential energy, mgh. And this is going to be equal to the kinetic energy of this block when it gets down to the bottom. So this is going to be 1/2 mv2 squared. So this is state 1, this is state 2. Okay. So from this, what we can do is we can, let's just leave this for now because we don't know exactly what we're trying to solve for yet. Ultimately, it's the height h. So, and in order to use this later, we actually need to solve for the v2 to plug it into the other one, the other equation. So this is going to say that v2 is going to be equal to the 2 times the square root of gh. Okay. Now, to go from state 2 to state 3, so 2 to 3, we're going to be conserving momentum in the x direction. So this momentum in the x direction, so we'll say that sum of the momentum in x in 2 is equal to sum of momentum in x in 3. This momentum in the x direction for this one is going to be m times v2 times cosine of theta, right? Because this only is conserving momentum in the x direction. Just like in the last problem, there's going to be some like recoil in the table in order to compensate for the velocity that's picked up. This kind of crunches into the ground in order for it to have no momentum in the y direction. So we have this angle of theta here, that the x component of the momentum is just going to be the mv2 cosine of theta. And this is going to be equal to the momentum in the next state, which is going to be capital M plus M times v3. Now, in order to go from state 3 to state 4, so 3 to 4, we're conserving energy again. So this is going to be 1/2 m plus m times v3 squared. And this is going to be equal to the work done by friction. So this is going to be mu times m plus m times g times the distance that it goes. This distance, capital D. Okay, I called it lowercase d here. So let's, what does it say in the statement of the problem? It calls this distance L. It calls this distance L. So we'll call this distance L. Okay, and we'll fix that here as well. So this is going to be the distance of L. Okay, so now we have a set of equations that we can use in order to solve this, where here's our first equation, because ultimately what we want is we want this height of h, which is actually itself capital. So we have height of capital H. So we can take this, plug it in here, then take this v3 and plug it in there. So let's see what we end up having here. So this is going to be square root 2gh times m cosine of theta is going to be equal to m plus m times v3. So we can take this m plus m and move it over here. So then we have v3 is going to be equal to, v3 is going to be equal to this. So v3. And then we end up having 1/2, and let's do a little bit more rearranging. So v3 is going to be equal to 2gl with a mu with a square root. So 2gh square root times m cos theta divided by m plus m is going to be equal to square root 2 mu gl. Okay, and then we can move some things around, square some sides, and so what we end up seeing then is that 2 mu gl times m plus m divided by m cosine of theta squared is going to be equal to 2gh, and then in the end what we can do is we can just cancel some things here and here. And so in the end, what we end up seeing is that this height h is going to be equal to mu L times m plus m divided by m cosine of theta, quantity squared. Okay, and that's going to be it for that one. So let's move on to the next one. All right, so the last of these momentum energy conservation questions is this pendulum that's got two pieces hanging off it where they explode, and we want to find what the angle that this theta 2 is going to be for this mass that's going to be on the right side. Okay, so what we end up having here is, here are our strings. So we're drawing the initial state here. So call this one state 1. So here's state 1. Kind of boring, nothing's happening. So this is going to be just at rest. Then state 2 is the instant that these blow up. So this is going to explode with some velocity. We'll call this this portion M1, call this one M2, call this V1 for our M1, call this M2, and this is going to be V2. And then the third state, we have this one. It's going to be at some angle of theta. This is distance S. This is our M1. This one, this is theta 1. This is going to be theta 2. Sorry, theta 2. And then this is going to be our mass. This is going to be our mass of M2. Okay. So conserving momentum from state 1 to state 2. So going from here to here is going to be, how do I draw this? I want to use the same colors. So going from here to here is going to be energy conservation. So, momentum conservation. So we're going from here to here, we're conserving momentum. It's P is conserved. P is conserved. And then going from here to here, energy is conserved. Energy is conserved. Okay, so let's set this up. So P1, sum P1 in X is going to be equal to sum P2 in X. So kind of boring state to start with. Starts with nothing going on. And then in the second state, let's call this the plus X direction. So then we have minus M1 V1 plus M2 V2, or M1 V1 is equal to M2 V2. Okay, so going from state 2 to state 3, we have to kind of be careful here, because what we end up having here is this is the distance S, and then normally this was hanging down before, the same distance S. And when we want to look at the height here, this height is what we're after. Call this H1. This is going to be a distance S times cosine of theta 1. S times cosine of theta 1, which says then that H1 is going to be equal to S minus, so this whole distance is S. So this is going to be S minus S times cosine of theta 1, or you could say that this is going to be S times 1 minus cosine of theta 1. Okay, so we have some energy conservation equations that we can get, where we say that mgh1, m1gh1 is going to be equal to 1/2 m1 v1 squared. Same thing with m2. m2 gh2 is going to be equal to 1/2 m2 v2 squared. Okay, and we can see that we're going to be canceling our masses m1s and m2s. Ultimately, we're going to have, here's our theta 1. Ultimately, we're going to have g times s times 1 minus cosine of theta 1 is going to be equal to, this is going to be equal to 1/2 v1 squared, and we have something similar for our second equation. G times s times 1 minus cosine of theta 2 is going to be equal to 1/2 v2 squared. Okay, so we have ultimately a system of equations here, because we know that these are connected to each other via this equation and then these two equations, because ultimately what we want to do is solve this system for theta 2, right? So theta 2 is going to be equal to, when we move this around, we end up having GS minus 1/2, sorry, we have an arc cosine here. We have this is equal to a cos of GS minus 1/2 V2 squared divided by GS, where V2 is going to be equal to M1, sorry, let's see, V2 is going to be equal to M1 divided by M2 times V1, and then V1 is really going to be equal to the square root of, or we could just do V1 squared, I guess. So let's do it like this. This is going to make the algebra a little bit easier. So I'm just going to square everything, keep some square terms in here. V1 squared is going to be equal to 2GS 1 minus cos theta. Take this, plug it in there. This says that this is going to be M1 over M2 squared. We get 2GS 1 minus cos theta. And then what we have in the end is that theta 1 is going to be equal to a cos of, let's see, do we have something interesting happening here? We do indeed. We have 1 minus, the 2's cancel. Oh, this actually works out pretty nicely. This is going to be M1 over M2 squared. GS's cancel. This is going to be 1 minus cosine of theta 1. And then that's it. Okay. So check my math here. I did the algebra really quickly, but that isn't really the most important part. As always, the algebra is less important than setting up the equations. And as long as you're understanding how you can apply conservation of energy, conservation of momentum to set up these equations, then you have everything you need. Okay, so that's going to be it for this one, guys.